All right, section 6 in chapter 2, talking about our two different types of formulas, our molecular formula. This is the exact number of each type of atom in a molecule. So, for example, water is H2O. We look at, this is an organic, there's an E there. Organic chemical benzene is C6H6. Or another example stemming from some biology, glucose, C6H12O6. Kind of a way that we can summarize what the molecular formula is. This is the actual formula. Molecules are always written in molecular form so that we see the actual ratio. Empirical formula is where we take a molecular formula and we reduce it down to its lowest common value. So it's the simplest whole ratio of each atom in a molecule. For some chemicals, it's going to be the same thing. So for water, that stays the same. However, for benzene, even though up here we had 6:6 ratio, if we reduce this down, our empirical formula becomes carbon and hydrogen. And then our glucose, we're looking at a CH2O. Sometimes empirical formula is helpful. This is actually what, if we were to try and experimentally determine our formula, we're always going to start with this, with the empirical formula. So this is experimentally determined. And it tells you ultimately what the simplest ratio of each atom is. Whereas in the molecular formula, this not only tells you the ratio of the atoms, but it also tells you kind of how many of each of those atoms is in a grouping, so is in a molecule. So we've learned now our kind of two different types of formulas. We've already learned about ions, so now let's put our ions together to try and draw out formulas. Okay, for ionic compounds, compounds made from ions, we're always going to write it in terms of its empirical formula, so its lowest ratio of atoms. So for ionic compounds, these are made from two or more ions, and it's always going to be a cation plus an anion. Okay, so we're taking something that forms a positive ion with a negative ion. Okay, opposites attract, so that shouldn't surprise us too much. All right, ionic compounds, another name for them is we also commonly refer to these as salts. So a chemist refers to salt as an ionic compound. When a chemist needs to refer to what the general population refers to as salt, we call that table salt. So we always write an empirical formula, and we're going to write the formula so that we have a neutral product in the end. We are always trying to get things equal and opposite. So if we take, say, sodium, sodium is in group 1A, it forms a +1 charge. And we add that to, say, chloride ion, group 7A, so it forms a -1 charge. These have equal and opposite charges, so when they combine, their formula is just a 1-to-1 ratio, so we have NaCl. This is sodium chloride. This is actually table salt here. We can have other compounds, say the magnesium ion, combining with the oxide ion. These are also equal and opposite, so when they combine, they're still going to be in a 1-to-1 ratio. When your ions, when your charges are not automatically equal and opposite, in order to determine the formulas, we want them combined so that they are neutral in the end. And an easy way to do this is, I call it the cross-charge method. And how that works is, we're going to look at an example here. We have aluminum ion, just 3 plus, the sulfide ion, just 2 minus. What we're going to do is we're going to take the value of our cation. That's going to become the subscript for our anion. The value on the anion becomes the subscript for the cation. So that when we combine these, we're going to have Al2, oops, I messed up my colors, S is green, and the 3 comes from the aluminum. The other way that you can do it if you want to set it up mathematically is you need to figure out how many aluminums of your +3, so number of aluminums plus our number of sulfurs times our -2. This has to equal 0. So in this case, we have 2 times a +3 plus 3 times a -2. We have a +6 plus a -6. That equals 0. This is particularly important because when we look at some ions like iron 2 plus, iron also forms a 3 plus ion. And if we were to combine this with, say, the oxide ion, we're going to get 2 different formulas. For our top one, they're equal and opposite, so we have FeO. In our bottom one, we have to have 2 irons for every 3 oxygens. And again, figure 2.11 shows the charges that your elements have. We talked about this in the previous video, but you need to know these. And that's where it shows your group number and its charge. When we have ionic compounds using 1 or more polyatomic ions, so we kind of deal with or treat our polyatomics as an entire anion. So if we looked at, say, potassium ion and the nitrate ion, we treat this NO3 as kind of one entity. That's an anion with a -1 charge. So they're equal and opposite, so we need 1 of each. So we need 1 potassium and we need 1 nitrate. If we have a polyatomic that has multiple charges to it, we still can do that cross-charge method. So the 1 from the sodium goes to our polyatomics. We only need 1 CO3. The 2 goes for the subscript as sodium. So we end up with Na2CO3. When we need to represent more than 1 polyatomic ion, in this case, we need to represent 3 nitrates for every 1 iron here. So we have our iron. We still keep our NO3 together, but we need to represent that we need 3 NO3s. So we put parentheses around them and the 3 on the outside. Sometimes people want to make the argument that you could write it this way, but this is incorrect in terms of formula because we want to show that this is 3 nitrates, not 3 nitrogens and 9 oxygens. So we always put our polyatomics in parentheses. So try this one out. Magnesium ion with the carbonate ion. Excellent. Hopefully you have an answer. We have 2 plus and a 2 negative, so they're equal and opposite. So we just need 1 of each. So we'd have MgCO3. So you want to, when you're working with polyatomics, you want to use parentheses to keep the polyatomic together. And as a reminder for our polyatomic ions, you need to know all of your polyatomic ions. In particular, you need to know all of them that are on your pre-lecture worksheet for Chapter 2, that second page. You need to know the name, the formula, and the charge. So that pre-lecture worksheet was designed to try and help you work on starting memorizing those.